For more than 2 decades, the International Space Station, the ISS, has circled Earth every 90 minutes, quietly carving a path through the boundary between our world and the infinite darkness beyond. It has been humanity's home in space, a laboratory of science, a symbol of unity, and one of the most complex machines ever assembled by human hands. Up there, above the weather, above the turbulence and noise of everyday life, astronauts have watched continents drift beneath them like ancient paintings and witnessed sunrises 16 times a day. In the silence of orbit, the ISS has become a place where humanity has learned, dreamed, and reached for answers. But nothing in orbit lasts forever. The ISS is aging. Its modules have endured decades of radiation, micrometeoroid strikes, mechanical stress, and constant pressurization cycles. Eventually, in the not-so-distant future, it must come down. Controlled, carefully, precisely, a guided descent to a remote section of the Pacific Ocean known as the spacecraft cemetery, far from shipping lanes, far from people, far from anything that could be harmed. Yet this certainty reveals a new, unsettling question. What if that controlled descent fails? What if the deorbit burn goes wrong? What if communication is lost at the critical moment? What if the ISS, a 400-ton behemoth of metal, solar panels, and pressurized modules, misses its target? It's a scenario that space agencies prepare for meticulously. But it's also a scenario worth exploring, not for fear, but for understanding. When the ISS reaches the end of its life, it will not simply drop from the sky like a falling star. The process involves physics, precision, and coordination across multiple nations. A series of engine firings, known as deorbit burns, will gradually lower the station into deeper layers of Earth's atmosphere. These burns must be timed perfectly, executed in the correct orientation, and monitored second by second. The ISS is not a small craft. Its solar arrays span the size of a football field. Its modules weigh as much as passenger jets. To bring something of this magnitude down safely, engineers must control every part of the descent. They must ensure that the station enters the atmosphere at the right angle, shallow enough to burn most of it up, but steep enough that whatever pieces survive the inferno fall into an uninhabited region of ocean. The chosen region is the South Pacific Ocean uninhabited area, a place so vast, so empty, so distant from civilization that it has become Earth's designated graveyard for spacecraft. Space agencies have sent dozens of satellites and stations there over the decades, but none have matched the size or mass of the ISS. The plan is careful. The plan is precise. The plan has been rehearsed again and again on paper, in simulations, in every control room that collaborates on the ISS. But plans require everything to go right, and space has a way of introducing surprises. To understand the risk, we must understand the fragility of control and orbit. The ISS is stable, but it is also enormous, a structure shaped like a collection of interconnected tubes and wings. Atmospheric drag at its altitude is tiny, but not zero, and solar activity can inflate Earth's atmosphere, increasing drag unpredictably. A stronger solar storm could alter its orbital decay just enough to complicate timing. Then there are onboard systems. Gyroscopes, thrusters, navigation equipment, and communication links must all operate perfectly during deorbit. A malfunction in attitude control could send the station tumbling. A lost connection could delay the burn. A software error could misjudge timing by seconds. And in orbital mechanics, a few seconds can mean thousands of kilometers of difference on Earth's surface. There is also the possibility, however small, of a micrometeoroid strike at the worst moment. Even a fragment the size of a marble can cause significant damage at orbital speeds. If such a strike compromised thrusters or power systems during deorbit, the station could begin its descent uncontrolled. None of these scenarios are likely. All of them are planned for, but they are not impossible. And if the station misses its target, the consequences become far more complicated. If the ISS fails to enter Earth's atmosphere at the intended angle, it could begin to break apart unpredictably. Pieces would heat, fracture, and shear off at high altitude. Some would vaporize instantly. Others, particularly the densest components, like gyroscopes, life support systems, and support trusses, could survive re-entry. Most would still fall harmlessly into the ocean. Earth is mostly water. Even an uncontrolled descent is unlikely to strike a populated area. But the key word is unlikely, not impossible. If the descent corridor shifts too far north or south, debris could scatter across regions that were never meant to be touched. Small towns, uninhabited islands, shipping lanes, fishing zones, or, in a very unlikely but not unthinkable scenario, the outskirts of major cities. The ISS would not crash as a single piece. It would fragment. Large chunks might break apart into dozens of smaller ones, each carving its own fiery path across the sky like a swarm of artificial meteors. The sight would be awe-inspiring. It would also be dangerous. Windows could shatter. Pieces could impact structures. Emergency services might be deployed to large debris fields spread across hundreds of kilometers. And investigation teams would be sent in to track down and recover hazardous materials or pressurized tanks that survived the fall. The aftermath would be chaotic, not apocalyptic, but serious, costly, and deeply unsettling. To understand just how violent re-entry is, imagine an object hitting the air at more than 17,000 miles per hour. The air in front of it compresses so rapidly that it heats to thousands of degrees. Metals glow, panels tear away, bolts melt, anything hollow crumples, anything fragile vaporizes. Re-entry is an event designed to destroy. But the ISS isn't made to withstand re-entry. It's made to survive in space. That means many of its components, thick machinery, tanks, structural beams, are tough enough to survive the descent. If the deorbit is uncontrolled, those surviving pieces don't follow a neat trajectory. They scatter like shrapnel. Some fall into the ocean, some into wilderness, some, if the angle is extremely unlucky, could land where people live. Again, the probability is low, but not zero. And with an object this large, the stakes rise. If the ISS were to miss its target, the world's space agencies would respond instantly. Tracking stations would calculate debris paths in real time. Coast guards and emergency services would be alerted. Nations along the trajectory would be warned to stay indoors, avoid certain regions, or suspend air traffic temporarily. Recovery teams would mobilize to retrieve surviving components and examine them for hazardous materials. Investigators would determine which systems failed, how the descent deviated, and what lessons could prevent such an event from ever happening again. In the aftermath, the world would debate what went wrong. Engineers would examine data. Politicians would question the risks. Scientists would refine future deorbit plans for satellites, stations, and orbital infrastructure yet to come. It would be a global moment, not of catastrophe, but of reckoning. The ISS has served humanity with grace, resilience, and brilliance. It has floated above our world as a shining laboratory, a symbol of international cooperation, and a testament to what we can build when we reach upward together. When its journey ends, The hope is that it ends with dignity, in a controlled descent into a quiet stretch of ocean, far from the world it served for so long. But even as we plan, calculate, and simulate every detail, we must accept a simple truth. Nothing in space is ever perfectly predictable. The ISS will come down. The question is whether it comes down exactly where we intend, or whether it reminds us, one last time, of the power and unpredictability of the frontier above our skies.